So I'll talk about some of the experiments that we have been doing with ultra-cold atoms in a simulating an atom-optic kicked rotor. So before starting my talk, I would like to acknowledge all the funding agencies from the past and the current funding agencies, which are on the basis of which I have built the laboratory from scratch. And there are many, many experiments that are going on. And all this would not have been possible without so many of my students who graduated. And currently I have four of them, Rejish, Shuvarti, and Joel and Monu are the current students. All these are graduated, and I don't think Florian would recognize Sumit from the past. Yeah. Yeah. So as you all know, by now you would have known what all things can be done with ultra cold atoms. So I've just given a few examples here. I mean, there are many, many more things that can be done. So I'm showing this because in our group, we are basically working on multiple projects focusing on using ultra cold atoms for building atomic clocks. I mean, the laboratory-based atomic clocks to do quantum simulations. And some of our work also focuses upon understanding the physics of Anderson localization. And there is some work which we have done and we would like to take it on for commercial deployment is this work using atom interferometry. So just a glimpse of the various things that go on in my lab. First, as I said, we use ultra-cold atoms. So there are three atomic systems with which we work in the lab. One is rubidium neutral atoms, strontium neutral atoms, and calcium ions. So with rubidium atoms, we have a very good, robust, and versatile machine with which we can do a lot of things, out of which one of them is to use these ultra-cold atoms, not in a condensate, well, also a condensate, but mostly with ultra-cold atoms. We do experiments where we simulate an atom-optic kicked rotor and study the physics of dynamical localization, quantum chaos, and so on. And for example, this picture is a picture of a momentum distribution of atoms. When the momentum distribution gets localized, as you can see, this is a semi-log plot, and you can see that it's an exponentially localized momentum distribution state. And this is a directed motion of a Bose condensate under the influence of certain time-dependent perturbation through an optical lattice, and so on. The other bigger project is using ultra-cold strontium atoms for two different experiments, two different projects. One is to build nodes for quantum information distribution. That is, the idea is to couple ultra-cold single strontium atoms to plasmonic nanostructures and basically do remote entanglement of different atomic systems. You can use it, for example, for networking of quantum computers. Like in classical computers, you put multiple processors together and build a cluster. One of the ideas is to be able to network a bunch of quantum processors with highly controllable and clean, pure qubits, less number of qubits, but more controllable and pure qubits. But you need a mechanism to entangle or couple these quantum processors, not through classical information, but through quantum information transfer from one node to the other. So that's one project. The other project is to build a strontium optical atomic clock with atoms, in strontium atoms in an optical lattice. But we are going to probably move this experiment to the National Physical Laboratory, where this was going to be pursued for timekeeping and, I mean, to build strontium optical clock for national timekeeping. With rubidium, we have done multiple things. The recent one was using a free-falling rubidium Bose-Einstein condensate and demonstrated the atomic gravimeter to measure gravitational acceleration that system would allow you to build a sensor that would measure gravitational acceleration to a very high degree of precision, which is important for many technological applications. One of them is, for example, to map minerals and even groundwater, other than many other strategic applications. That demonstration we did with the same machine that we have, and now we are looking at translating that into something which one can use it for field applications. The other one is very close to what Florian talked about yesterday is to, I mean, we are not working on it right now, but we were, as part of our atom optics projects, we demonstrated and used quasi-continuous atom laser. I mean, it's basically a stream of coherent atoms which are extracted from a reservoir of Bose condensate. And you can see that this picture is a beautiful demonstration of how matter waves behave like light waves. Like, for example, when you put a laser beam through a grating, it diffracts depending upon several conditions. You can be either in the Raman-Nath regime or the Bragg regime. So this diffraction is in the Raman-Nath regime. So you see that when this coherent beam of light interacts with a standing wave of light, which acts like a grating for matter waves, you see a nice diffraction pattern. Now, the current project is basically, this is more of this is more for developing to demonstrate a working quantum computer with ions, calcium ions. As you can see, these are individual calcium ions, light emitted from individual calcium ions from trapped in a linear trap, which basically you can imagine it as a bunch of masses which are suspended on springs, and this chain would act like you can imagine it as a molecule, and you use common modes of vibrations to couple neighboring qubits or any qubits in this particular chain to build to be able to apply 2-qubit gates, which is a necessity to build a universal quantum computer. And we can trap up to 25 ions now, and we are currently working on optimizing the gate operation, single qubit and 2-qubit gate operations. So that's going on this project is going on a rapid pace. But what I'm going to talk about is something else. Okay, this is another project. So one of my BSMS students this year has used that same rubidium BEC machine to demonstrate capture of single atoms in an array of optical lattices. So he used an acousto-optic deflector to generate a linear array of optical tweezers in which this is a fluorescence from neutral atoms that are trapped, and we think we have trapped single atoms, so more experiments are going on, and he has submitted his thesis, so we might stop this project at the moment and move on with other things. Anyway, so I'm going to talk about these the experiments that are related to quantum simulations with these ultra-cold atoms. And this work is in collaboration with my colleague Santanam and his students. Okay. I think some of the speakers already talked about these flow case systems and many interesting things that can be done with this in the last couple of days. But just for the interest of some of for the students, I'll start with some basics and then move on to what we did with these ultra-cold atoms. Okay, so a kicked rotor is nothing but, classical kicked rotor is nothing but a particle which is confined to be rotating, moving on a ring. And then if you periodically kick that particle on this ring, then it basically becomes chaotic under certain conditions. So you can write the classical Hamiltonian where you have the momentum. Okay, this P, you read it as an angular momentum here. And then you have this perturbation, which is basically, it's not a perturbation, it's a strong perturbation or whatever. I mean, it's a disturbance which cannot be treated as a perturbation. And you do that periodically. And you can calculate the phase space for such a system, and you can map the momentum and angle as a function of this K, which is called as a kicking strength. When you do that, initially all the trajectories in phase space are pretty predictable and pretty uniform. But as you keep increasing this value of this kick strength beyond a certain number, like close to 1, then all these trajectories start breaking, and then the motion becomes completely chaotic. And then in this region, the particle motion is more or less like a diffusive motion. You can calculate what would be the energy gain of that by calculating the RMS of this momentum. And what you notice is that for kick strength, which is larger than the minimum needed to make this motion chaotic, the energy starts growing linearly. And this is what is the diffusive limit of this motion. Now, you do the same thing for a quantum mechanical system. You start with a Hamiltonian, and then since your perturbation is periodic in time, this system is basically like your particle moving in periodic potentials in real space, right? And your solutions are similar to block functions, what you see for electrons in a periodic potential. And you get this expression for the stationary solutions, which is basically time periodic. You just, it's exactly like your block functions. One can calculate the energy growth of such a system by looking at how the system evolves under this operator called as a Floquet operator, which is this periodic kicking of the system. And you calculate the transition rate from different states that the system is allowed to move in this phase space. Then something interesting comes out. What happens is that for a classical case, your energy grows linearly. But for a quantum mechanical system, it does grow linearly initially as a number of the kicks that you give to this system. But after a certain time called as a quantum break time, your energy starts saturating. And if you look at how the momentum states that this system is mapping, system is going through, all the momentum states that the system is going through, you will see that in momentum space, the energy, the system kind of gets localized, meaning there is no more growth of energy, and then all the system kind of interferes in such a manner that it gets localized. Now, this is very similar to what happens with electrons in a disordered medium, which is basically given by the, it was predicted by Anderson, and there is a lot of work that is going on in different dimensions, what happens to this localization. This is similar to what happens there, but it's called as a dynamical localization. It's not localization in real space. Now, one can simulate such a system using ultra-cold atoms. And the way it is done is you take a bunch of cold atoms and you subject it to, you put them in a periodic potential, which is generated by interfering light. You put a standing wave of light, and light which is not resonant with any of the atomic transitions, but far off resonant. And then because of AC Stark shift, wherever there is an intensity maximum or minimum, depending on which side your light is detuned from any of the atomic resonances, you can either get a potential maxima or a minima. Now, this system is similar to the kicked rotor that I talked about, where the particle is confined to move in a circle. So here the conjugate variables are basically, in this case, the atoms are seeing this periodic potential in terms of this potential that is varying in space. And you can write the Hamiltonian and map it to the kicked rotor Hamiltonian. Now, the good thing in this case is that by just by playing with the parameters of this standing wave, you can tune the kick strength, you can tune the scaled Planck's constant and so on. So for example, this is the Hamiltonian that you write here for such a system. And the kick strength, for example, is dictated by the intensity of the light. In this case, it's coming here through the Rabi frequency, and how far the laser is detuned from any of these atomic resonances. Now, when you scale that Hamiltonian, you can scale this Hamiltonian and you get all these parameters. You can have a control on the kick amplitude by just changing the how deep the potential is, and by changing the time period between these kicks. Now, the conjugate variables that are there in this for this particular Hamiltonian are this phi and rho. And by changing this time period, you can change the scaled Planck's constant, and also you can change stochasticity parameter, the kick strength that I talked about, which decides whether you are in a chaotic regime or not. You can do all this and study all the physics of this kicked rotor. Now, this model was first demonstrated by Mark Raisin's group in 1995. Ever since then, there has been a lot of work that has gone into this, and people have studied many, many things. So, yeah, so we have these two things in our control. So we can change the period of pulses, we can change the intensity of these pulses and change those parameters and do a lot of things. Now, these are experiments that are done in the lab. So this is a cloud of cold atoms when it is not subjected to this periodic perturbation. So the momentum distribution is basically Gaussian. It's a thermal cloud. But as soon as you subject this cloud to periodic kicks, those standing wave potential, and after a while, when you look at the momentum distribution, you can see a nice localization. So this doesn't expand anymore. And if you plot the momentum distribution for that, you get this distribution. Now, if you look at how the energy is growing as a function of the number of kicks, you see that for a classical case, you expect that to grow linearly, which happens until a certain number of kicks. And beyond this so-called break time, the energy starts saturating. It doesn't increase anymore. Now, what all can be done with this? So here are some examples. So one can study the transition from localization to delocalization. You can basically extend the dimensionality of the system by bringing in a set of kicks whose frequency is incommensurate with each other, and you can increase the dimensionality of the system. You can study quantum ratchets, and you can also use it to study the fundamentals of the mechanism of decoherence in any quantum systems. You can use this as a model system. Now, we have done a couple of experiments, and here is the machine which we use for different experiments, including the one which I'm talking about here. And these are the classic pictures of what you would have seen everywhere of a rubidium, of a Bose condensate. So these are the distribution, thermal distribution. As you go through the phase transition, you see that the density distribution starts peaking up. And we use a crossed optical dipole trap where we capture the atoms from a magneto-optic trap into the crossed optical dipole trap, and then we do the evaporation by by doing this forced evaporation. And yeah, I don't have to tell all this because you know that in order to get into the Bose condensate regime, of course, you need to start with bosons, and you need to get to phase space density where the interparticle separation is of the order of the de Broglie wavelength of these particles and so on. And then you get to these particles condense into one momentum state, and you get a giant matter wave out of this. Normally, the process to make a Bose condensate or even Fermi gases is that you start with a magneto-optic trap, which is comprised of 6 laser beams. You capture large number of atoms of the order of a billion or so at few hundred microkelvins in this. Then you have to do use processes where you force the atomic sample to cool down without using lasers typically, without using resonant light. And there are multiple ways to do. You can spin polarize this sample and trap in a magnetic trap, or you can put them in far off resonant traps using this laser light. And then you force the atoms to basically get into a regime where the phase space density increases and you get to the Bose condensate. In this evaporative cooling, you rely upon chopping of the Maxwell-Boltzmann distribution's tail and let the remaining atoms rethermalize through good collisions, and you keep increasing the phase space density, of course, at the cost of losing the number of atoms, but you start with a billion atoms and you can be left with a few 100,000 atoms or below 100,000 atoms, which is enough for doing a lot of things. Yeah, so this is how, okay, this is for the students. An animation of how it is done, but this is for a magnetic trap in our earlier version. So you start with the rubidium, which is heated in some part of the chamber. You generate an atomic beam. There are multiple ways to do it. The way we do it is this. So you then slow down the atoms from a few 100 meters per second down to 20 meters per second using what is called as a Zeeman slower, where you have resonant scattering of light from atoms, and then you capture them in a 6-beam magneto-optic trap like here, and you get about 1 billion atoms at a few 100 microkelvin. There is a small error in this. The atoms don't go out of this. Anyway, so, and then you spin polarize this atom if it's a magnetic trap, like in this case. You spin polarize all these atoms and then transfer them into a magnetic bottle or a magnetic trap. There is no light anymore. You have only magnetic trapping. Then, of course, the phase space density is very low, 10 to the power -6 or -7. Now you need to increase the phase space density. The way it is done is through this forced evaporative cooling. You blow radio frequency and flip the spins and throw the hotter atoms out and let the atoms rethermalize and get a Bose condensate. And then you can do all your physics experiments. And then for diagnosis, you shine a pulse of light and and measure the density distribution of the atoms on some detector like a CCD camera. And you do all the analysis. For the kicked rotor experiments, we generate that cold sample of atoms, not evaporate them until below the phase transition temperature, but just a little bit above to a few microkelvin. And then we drop them on a standing wave, which is pulsed using what we call as acoustoptic modulators, and you can control the on time and off time of this optical lattice. And then after that, they are dropped and you image the density distribution of this. So the first experiment that we did using this system is to engineer the bath to which these quantum systems interact with and change the functional form of the decoherence itself. So if you look at that density, if you look at that state where the momentum distribution is localized, it's very sensitive to anything that any external decohering mechanisms. Like for example, if you put off resonant light, these atoms are going to scatter photons, and then the decoherence sets in, and the momentum distribution that's localized, it starts delocalizing. And people did demonstrate this by doing a couple of things. Like for example, if you bring in randomness in the kicks, that's like a perturbing mechanism. If you put resonant light, that's like a perturbing mechanism on this momentum distribution, which is localized. And the energy growth initially, which was saturating, starts increasing, and then you start pushing the system towards the classical regime. Now, all this is fine. In all these experiments, of course, it was clear that the decoherence was following an exponential form, which we all know. So decoherence in any quantum mechanical system, most of the systems, they kind of decohere exponentially. Now, what we did was that, so the way this decoherence is setting in, as I said, you can bring in randomness in the kicks, or you can have some other mechanism, like if, for example, depending on what kind of systems you have, in this case, it's neutral atoms, so they interact very weakly with the environment, as opposed to, say, ions, for example. Now, you could bring in any, so your environment could be anything, magnetic fields, electric fields, or light, etc. And also in this particular system, you also have the periodicity of the kicks. If it is not uniform, then the system starts decohering. Now, what we did was so if you had a periodic case, you have the pulses like that coming one after the other with definite intervals. Now, if you start jittering these pulses, it is going to kill the decoherence. And you can, in a normal case, when this noise in this pulses is like uniformly distributed in the power spectrum, then it starts going exponentially. But in our case, what we did was, there were some predictions in the past that if you bring in certain type of noise in the amplitude of these kicks, like for example, if you bring in Levy type of distribution in the amplitudes of these kicks, then you could actually make the decoherence follow non-exponential behavior. But since technically it was difficult to increase the amplitude, so vary the amplitudes, which vary, whose distribution would vary according to this functional form, what we decided was to just skip the kicks in such a manner that the gaps between these regions where you're skipping the kicks follows this kind of distribution. And this alpha is basically this exponent here on this, in this distribution of this, the time intervals between the kicks. So we brought in this, and what happens, I'll show you when you do that. So of course, I mean, you start with that Hamiltonian, and then here in this case, just to simulate, to include the absence of the kicks or presence of the kicks, you introduce this factor G here. And then the distribution of this kicks, you make it follow this exponent, I mean, so this kind of a distribution, which is a power, which follows a power law. Then you write the Floquet operator for such a system, where you write the evolution of the system during the kick, when the kick is not there, and again when the kick is there, and so on. So you can write the operator in this fashion. And you calculate the energy growth of such a system by calculating the RMS growth of the average energy. And you can, in order to find out what the coherence does for such a system, then you calculate this two-time correlation functions and these decoherence factors. And what happens is that, okay, I'll not get into all these details. What is important is that the decoherence, actually, depending on what your alpha is, whether it's smaller than 1 or greater than 1, for when alpha is smaller than 1, it is completely non-exponential. Of course, experimentally, it is difficult to fit the data to such a complex function. This is some, I forget the name now, it's some Mittag-Leffler function or something. And then for alpha greater than 1, it follows an exponential behavior as a function of time. So that's the key takeaway. And you can, even the energy growth, depending on what your alpha value is, the exponent of that distribution, it is either when alpha is greater than 1, it follows a linear form, and when alpha is less than 1, it's non-linear in nature. Now, these are the results. Now, if you have a complete random distribution of these kicks, the energy growth is more or less follows what you expect for a classical system. And when you have a completely periodic case, the energy initially grows a little bit and then saturates. So this is a completely localized state, and this is a completely delocalized state. So for this is a localized state, this is a completely delocalized state. And then in between, you get a subdiffusive behavior. This is a complete classical diffusion, this is subdiffusion, and this is localized state. And if you look at how the this delocalization happens as a function of time, for a periodic case, it kind of remains whatever the localization just remains as a function of time. And when you have a random noise, the delocalization follows, this is a log-log plot. So the delocalization follows the usual exponential behavior. And for in between, when your alpha is less than 1, if you look at the delocalization, it follows a power law. So this is like by playing with the statistics of the this periodic perturbation, you can actually think of it like playing with the statistics of the environmental noise that is influencing your quantum system. So in a way, you can think of, one can then think of playing with the noise characteristics of the environment to play with the decoherence of the quantum system. So this is one experiment. One can also control this localization length by doing some more additional things. Like for example, one of the things that can be done is, if you look at the momentum distribution here, you can actually increase the delocalization, the localization length. Okay, so in our case, what we did was after a certain number of kicks, you skip some kicks. So theoretically, to take that into account, it's like uh, introducing kicks with a negative value, which essentially means that what you do is that you give certain number of kicks and then skip certain number of kicks. So what happens is that during that free evolution, these wave functions in this momentum space, they pick up phases which are like multiples of 2 pi, and then you basically end up with the same state, and you play with the interference of these wave packets by playing with the uh, phase evolution time that you get. And you can basically change the localization length. So this is for the case where you have skipped 2 kicks in between, and you can basically change the how far the system gets localized by just playing with this. So this is for different values of the number of kicks that you skip in between. You go from you basically increase the amount of energy that the system kind of absorbs from your external perturbation as you do that. We use this same system to do some measurements of how a Bose-Einstein condensate, when it is released from the trap, typically when you, for many of these experiments, what you do is that you have the condensate in some confining potential, you turn off this potential, and then you do all your physics experiments with the condensate that's come out, that's released from the trap. Now, for certain experiments like atom interferometry and all that, what happens is when you release the condensate, it may move a little bit here and there depending upon how well you design this trapping potentials. There could be some perturbations from outside which will move the condensate a little bit. Now, this is sometimes sometimes it's not very good to have such a thing, or sometimes you need to know how much it has moved. So using the same system, we have done this measurement of these small motions that your BEC gets when it's released from the trap. The way it is done is you have this cloud, and then when you have the cloud in this periodic potential, either if your lattice shakes or if your cloud shakes, what happens is that okay, these are wave packets actually. Since we used a Bose condensate for this experiment, the condensate kind of diffracts into different momentum orders, and the amplitude in each of these diffracted orders, so the amplitude in each of these diffracted orders, if you plot them, it again exponentially localizes. Now, if you have any small motion, what happens is that this localization, the symmetry changes. So you get the momentum distribution kind of shifts in either of the directions, depending on which way the cloud has moved. So the starting velocity of the cloud decides whether the localization is exactly centered or it has moved. Now, using this distribution, the asymmetric nature of this distribution, we have done measurements, measurement of tiny motions, like by changing this lattice velocity in either of the direction. You look at the how the symmetric nature of this distribution has changed, and you get a point where you can actually matches with the initial velocity of the cloud that has come out of the trap, and you can do tiny measurements like this. In this case, we could measure velocities up to a few hundred micrometers per second when the cloud has gone out of that. Yeah, so these are some of the experiments that we have done using this condensate, and now we are doing some more things, but not with a kicked rotor, but in momentum space lattice, some quantum simulation experiments and so on. It's not completely done, so I'm not presenting that. Yeah, so that's it.
Sir, in making of periodic potential, we basically use detuned laser light. So which kind of detuned laser light is basically use a red detuned or blue detuned in making a periodic potential?
So for these experiments, it was red detuned.
Red
For
detuned.
most of our experiments, it's red detuned.
Okay.
You can also use blue detuned if you want, but
And also we use a uh, TM00 mode, so basically Gaussian mode. So we can also use a higher modes of trapping potential.
You could, but you need to take care of accounting for the nature of the mode in your. So it's going to decide how the potential is, right? So axially, it is Gaussian in this case. Now, if you use higher order modes, then you have to worry about which mode it is, and accordingly, you have to take into account how your atoms are seeing the potential, and you get into more complicated situations.
Okay, I have one question. How to make trapping potential to trap the atom experimentally?
There are multiple ways. So either a magnetic, you can do magnetic. So depending on whether it's a neutral atom or an ion, the trapping schemes are different. So if you have neutral atoms, then you use magnetic forces or uh, forces generated because of the AC star shift.
For achieving BEC after mode.
You can use both a magnetic trap or an optical dipole trap to get a BEC. You can use either of them depending on what atom it is.
Okay.
Yeah.
Thank you.
Umakant, very nice. Very nice talk.
Thank you. Yeah.
So, okay. So when you are implementing this Levy distribution, you impose some cutoff at within some frequency range and stuff like that, at least for the lower part, because parallel distributions.
Yeah. So, for example, if you have only limited choices, it's all decided by your exponent alpha. And within that also, you have limited range of parameters to play with experimentally.
I'm just talking about the frequency distribution that you put in.
So that is decided by the Talbot time of the phase evolution of the atoms. So the periodicity of the kicks, that decides your kick strength and other parameters. So you have to fix all of those first. It kind of gives you limited space to play with.
Okay. Yeah.
Like like these things, the time period between the kicks and the stochasticity parameter, that you have to fix. You don't have much range to play with. Yeah, because otherwise you won't be in the chaotic regime and many other things go on. So you have to ensure all that is taken care of. Yeah.
Can we ask here what is the route to chaos? How the frequency are generated, and then you get the chaotic state?
I didn't understand the question.
Okay, so maybe we'll talk later.
Yeah. Okay.
Yeah. Thanks for the nice talk. I'm just asking that when you are kicking the lattice, then does this dynamical localization depends on the kicking, how many kicks you are giving? Like suppose the localization of the like in the momentum space, it can have at the 30th kick also, at the 50th kick also. So
you can change that with these parameters, the kick strength and the stochasticity parameter. You can change with those, where the break time can be decided by that. It's decided by the scaled Planck's constant.
Okay.
Where it starts, where there is a crossover.
So like if the state is localized, then is it localized at 30th kick also and like 50th kick also? It will.
You can do that. You can change that where it gets localized.
Okay.
By playing with the parameters. So that's why it gives you a lot of control on going into different regimes for that system experimentally. Yeah.
Very nice talk.
Thank you.
So all these experiments assuming single particle physics.
Yes.
So you don't think the interactions are modified, or what do you see?
So what we do is, in order to not have the influence of this interactions between the particles, you let this is a thermal cloud. But when we are doing experiments with the condensate, we ensure that the condensate kind of expands a little bit before we start, so that you don't care about, the interactions don't play much role. But for some other experiments, we actually want interactions that I am not talking about here. It's when you do these simulations in momentum space lattice, you actually want this interaction. So you do all this in the trap when the cloud is confined. They have some effect, interactions do have some effect, and you want that.
But I imagine they're going to make the localization even better, or has anyone studying what is the role of interaction with these kicks?
I don't know what would happen when the interactions set in. Yeah, possibly. Yeah.
Hello. Hello, sir. I want to ask that when you are moving mod, you were saying you are getting micro motion. So, is there any way you are reducing that micro motion?
No, in that experiment, the interest was not to reduce. Okay, well, ideally you don't want to have that. But even if you have that, you need to have a way to estimate how much it is so that you can take corrective actions.
And this micro motion is because of this we are
Not the micromotion in the sense of these ions in an ion trap. It's this small initial motion that you get when it is suddenly released from the trap.
So, I mean, you showed mostly this momentum distributions. And did you also look at the position distribution, like how that? Because that also looks.
Yeah. So we don't have the resolution to look at the position distribution at the scale of the lattice wave, the size of the lattice, but overall we can, okay, this is what you get, I mean, the images, and then you can look, this is what is the position distribution, essentially. But we didn't do a complete analysis of the position distribution. Yeah, data is there, yeah. But what people did do is that in real space, those were the first experiments that were also done, not the kicked rotor, but in real space. What you do is that you put a potential and you introduce randomness in the optical lattice potential. And they did so these were experiments done in France in Paris, by Alain Space Group, where they looked at the localization of the position distribution. So that's in real space. That's like direct replica of the Anderson localization. This is dynamical localization. Yeah. Yes. So that asymmetric localization is that. Okay, this, for example. You see, so these are for wave packets with very narrow momentum distribution done with a Bose condensate. If you could do this with thermal atoms also, and then you will get a continuous distribution, like in this case. This is a continuous distribution of the momentum. You can make it asymmetric.
But the peak is still at 0.
No, you can make the peak non-zero. It could be a localized state moving slowly, for example.